Hello everyone, I'm Saib Deshmukh and I welcome you in the video of application-aware routing. As you know, standard protocols like BGP or OSPF are great at finding a path, but they are all or nothing. They can detect a total blackout, but they are blind to brownouts. An application-aware routing is an app route policy that allows the SD-WAN fabric to monitor the quality of network paths in real time and do SLA-driven routing across the best available transports. R relies on BFD to detect performance issues such as packet loss, latency, and jitter on the overlay tunnels. Upon degradation of the performance of specific tunnel, traffic is going to move to another path. These policies are configured on manager and enforced onto the controllers via netconf. Further, controllers push the policy as a form of OMP update to manage router. These policies are only configured for the traffic that is coming from service side only. And when we define the policy, we have to mention the VPN and which site we want to attach this policy to. To understand how this policy works, we have to understand what role BFD plays in the SD-WAN topology. Here, we have two sites, each having two transports, MPLS and Biz Internet. Using these transports, and OMP information received from the controllers, these routers form IPsec tunnels with each other. Over these IPsec tunnels, each WAN edge exchange BFD packets, and other side would reply back immediately without processing heavily. Simply said, BFD works in echo mode in here, and this behavior is automatically enabled and cannot be disabled. These IPsec tunnels are up based on BFD multiplier. First, we establish our timeline. In a stable environment, BFD hello packets are sent and received at a steady pace. Here we have a BFD hello interval set to 1000 milliseconds. This means every single second, the V8 sends out a probe to verify the path's health. As long as these probes are returned, the tunnel remains active. However, things change when an indirect failure occurs in the WAN circuit. Notice that after probe 5, the replies stop coming back. Because we have a multiplier of 7, the router begins a countdown rather than dropping the link immediately. It is looking for 7 consecutive missed probes to confirm this isn't just a temporary blip. Once 7th probe fails to return, the threshold is met. The tunnel is officially considered down. It is at this exact moment that the SD-WAN fabric will withdraw this path and trigger a reroute to a healthier transport. To make intelligent routing decisions, the SD-WAN fabric must constantly calculate the actual quality of the path. It does this by analyzing the individual characteristics of every BFD exchange. As the first BFD probe returns to the site 1, the router immediately calculates the health of that specific moment in time. By comparing the transit and receive timestamps of the single packet, the system determines the current loss, latency, and jitter for this initial sample. A moment later, a second probe completes its journey. The fabric now has a new set of data points. It doesn't just look at these in isolation, it tracks the variation between BFD and BFD2 to identify trends like sudden spike in jitter or creeping increase in latency. By constantly refreshing these metrics with every BFD reply, the WAN edge maintains a real-time scorecard for the tunnel, allowing application-aware routing to stay ahead of network brownouts before they impact the user experience. While BFD probes gives us instant data, application-aware routing needs a broader view to make stable decisions. This is handled through poll intervals. By default, the VH groups BFD data into 10 minutes window called buckets. If our hello interval is 1 second, that means a single bucket contains the performance data of 600 individual BFD probes. This provides a statistically significant sample of how the WAN circuit is performing, filtering out one-off spikes that don't represent a true network issue. The final step in the performance calculation is the apt out multiplier. By default, the system looks at the last 6 buckets to determine the overall health of the path. As each 10-minute cycle completes, the oldest bucket is dropped and a new one is added. The fabric then calculates the mean or average of the loss latency and jitter across this entire hour-long window. This mean is the magic number. It is this value that our policy compares against your application's SLA. If the mean latency across these buckets exceed your threshold, only then will be the fabric trigger a path change. This ensures your traffic only moves when there is a sustained, verifiable degradation in the WAN. Now, let's put the theory into real-world context. In this topology, we have our WAN edge router sitting at a branch office, connected by two distinct paths, a premium MPLS circuit and a standard business internet link. Under a normal conditions, our R policy is configured to prefer the MPLS circuit for voice and video because of its guaranteed delivery. However, from the perspective of the WAN edge, a up status on the interface isn't enough. The router is constantly interrogating that MPLS tunnel using BFD probes to see if it is actually living up to its SLA. But what happens when that MPLS circuit doesn't fail completely, but starts to brown out, experiencing jitter or latency spikes? How does the router decide when the MPLS link has officially lost its privilege to carry our most important traffic? To answer that, we have to look under the hood at how the router actually calculates the performance over time. This brings us to the sliding window. Let's take a look at how our policy actually thinks when a circuit starts to degrade. On this chart, our SLA threshold is set to 100 milliseconds, marked by the horizontal black line. In poles 1 through 5, the circuit is healthy. You can see the light green bars, the actual latency, sitting at a rock solid 20 milliseconds because the performance is consistent. The dark green bars, the mean latency, match it exactly. Now look at pole 6. Something goes wrong, and the actual latency spikes to 200 milliseconds, which is double our allowed limit. In a basic setup, the router might panic and shift traffic immediately. But R is smarter because it uses a sliding window average that one bad pole is averaged in with previous 5 good poles. This keeps the mean latency at only 50 milliseconds, well below our threshold. As we hit pole 7, the actual latency stays high. Our mean latency is climbing, now hitting about 80 milliseconds. But we still haven't triggered a reroute. We're essentially giving the circuit a grace period to see if this is just a momentary blip. It isn't until pole 8 that mean latency have finally crossed that 100 millisecond line. This is the exact moment the R policy declares the path out of SLA and shifts your critical application traffic to enter a better circuit by focusing on the dark green mean bars rather than the light green actual spikes. We ensure the network only reacts to sustained degradation, preventing the flapping that happens when a router switches path back and forth too quickly. Here, I'm going to apply this in practical example. We have FTP server running in DC and site 4 WAN edge router is going to try to access it. Our goal is to prefer MPLS path, but if defined SLA threshold crosses, we want it to do some backup option, maybe do a load balancing. To start with, we are to create list. Here I'm going to create application list. We're going to name it FTP, and in application section, I'm going to recognize that application. Then we are going to create site list. We have created a hub site with site ID 1 and spoke site with site ID 3 and 4. As I told you before, that policy define needs a VPN as well, so we are going to have a VPN list as well. Here we have VPN list defined. In step 2, we need to define one more list, and that is SLA class. Here we are creating SLA class for FTP traffic with loss 1 and latency 150 milliseconds. This SLA class is going to be mentioned in later our policy and act as a threshold for our FTP traffic. In step 3, we create a policy itself. We start in by selecting custom options and create a new policy. Give the policy a name and description. Next, we define the sequence rule. Under match conditions from the application list, we'll search for and select FTP. Once the traffic is identified, we define the actions. We'll navigate to the action tab and select an SLA class list. To further optimize, we'll select a preferred color, setting it to the MPLS. And we can also add a remote preferred color such as BIS Internet, providing a secondary path if the primary is unavailable. Finally, we'll set the when SLA not met behavior to load balance to maintain connectivity even under suboptimal condition. After reviewing our match conditions and actions, we save the rules and then overall policy. This R policy is now ready to be included in our master centralized policy and pushed out to the WAN edge devices. To use our R policy, we need to mention it in the main centralized policy. To do that, edit the main centralized policy and add that policy in data policy section. Then apply this policy to spoke sites and VPN1. Hitting activate means the policy will be pushed down to all the controllers. We can also see what the new config is being pushed by clicking the config diff button. Config highlighted in green is a new configuration that is being pushed. As you can see, it says the configuration is push is successful. The policy configured on manager have been pushed to controllers. This is the details of the policy. As you can see, it matches the FTP traffic and action is to prefer the MPLS color and backup is BIS Internet as well. Here, the controller pushes the policy with the help of OMP update, and these are details. Notice the name saying from vSmart. That means it's saying that these policies have been received from the vSmart. Verification can be done using the command that you are seeing on the screen. In the output on site 4 WAN edge router, you can see it is showing MPLS color is preferred. So for the FTP traffic that is sourced from site 4 WAN edge router, specifically speaking VPN1, the traffic will take the path of MPLS to go to destination of that FTP traffic. Thank you for your time, and I will see you in the next video.